Robots among us. I hope that makes you a little bit scared. At least it does to me. But I have to say, it also makes me a bit envious, right? I'm a computer science student, or not student, I used to be a student, and I never got to play with hardware, right? I'm always envious when I look at these guys and their toys, right? Because all I have is software. But this is not all you're gonna see today. I was told today we have a highlight. We have our very own G1 PO, which is a robot humanoid. Some people get it, nice. Humanoid robot from China, owned by TNG and programmed by these guys. Now, the question that's asked by the talk is, when do we have robots in our home, right? And this is something I think that all of us kind of desire. It's your own helper and everything. These three speakers will start with a market overview, which I think is going to be valuable for most of us, right, to understand what's happening on this market. They're going to give you an overview of how do we actually train robots. And then talk about vision language action models, I hope that was correct, for human-robot interaction. Now, we have an all-star roster of speakers today, so I hope you guys are looking forward to that. We have Dr. Sven Rohr as an associate partner at TNG. He supports our ML teams internally and at customers. He operates the TNG's GPU cluster and trains TNG language models.
Da hast du dir aber was ausgedacht, wow.
We have Dr. Florian Garter, who's an associate partner at TNG as well. He's specialized in software project analysis and due diligences. He drives robotic projects with TNG Innovation Hacking, if you guys maybe know that. You saw, I think, an exhibit of those. And they combine LLMs with RFMs. And finally, we have Thomas Endres, managing partner at TNG. Now, besides his regular work, which is already keeps him busy enough, he's deeply involved in the naturally, right, in the innovation hacking prototyping, and he supports with AR, VR, AI, and gesture control projects. Now, these guys have deep expertise on these topics, right? They've worked on them on a very long time, so I hope you're all gonna join me, giving them a very warm welcome.
Thank you, Valentin.
Before you guys start, just one organizational note, questions in the end. And with that, I'm going to give it to you.
Okay, so thanks for joining us today. And you actually, Valentin, you forgot about one of our team members. And this is G1 PO, our technology ambassador, who conveniently has a duck on his head right now. I don't know why, but he's going to join us on stage, I would say. So let's give him a warm welcome as well. And he was already on stage this morning, but he was pretty drunk, so he did not do it very well. But I think he managed to get sober again. All right. So maybe you want to come up front and turn around. Come on. Thank you. Okay. So the question now is, what do we want to talk about today? So one thing that we want to show you at the beginning is the history of robotics, so how it all started, how it evolved, and things like that. Then we are going to talk about the basics of robotics so that you better understand our last part, which is about how you can train a robot, especially with robotic foundational models. So now let's dive right in. And since Zora was released just a few days ago, I thought, hey, let's do some AI slop at the beginning of every of these chapters. And we'll start with this one.
And we start telling you a little bit about the history of robots. The first idea of a robot dates back to antiquity, where in Europe and in Asia, people created mechanical devices that somehow resembled human beings or animals. And one idea that I'm very fond of is the idea of Talos, who is a giant bronzen warrior who patrolled the island of Crete several times a day in order to protect it. And by the end of the 15th century, Leonardo da Vinci was one of the first people to really systematically study biomechanics when he created the Automata Cavaliere. This is a mechanical knight that was probably never really built, but Leonardo used it to demonstrate how human motion could be achieved from mechanical parts.
In 1785, the power loom was invented, and this is one of the prime examples of
the first industrial automation done in the Industrial Revolution. It was invented by John Cartwright, and it was really a stepping stone back then. And we skip ahead 100 years. And around 1950, a group around Alan Turing and John McCarthy basically invented artificial intelligence. What they did was they built the mathematical foundations for machine learning. Also, Alan Turing invented or proposed the famous Turing test to determine if a machine can behave like a human in text-based conversations. Okay, few years into the future, Unimate and Puma, those are the first real industrial robots which could be freely programmed to perform specific tasks for industrial applications. This is Unimate. Doesn't look very modern, but back then it was really innovative. And Puma is the name stands for Programmable Universal Machine for Assembly, and it is exactly that.
Yeah, of course, the industrial robots started to evolve back then, but we'll have a look at another thing that happened. So we sent robots to Mars, to other planets, to really roam around for themselves and find some interesting samples. And this was, of course, also in the field of robotics. And now we're starting into the 2000s, and this is where the first humanoid robots came out. So the Honda Asimo, there's a famous video of him falling down the stairs. And we also have the Now robot, which came out in the year 2008. And this is a significant step forward. It was a little guy, like something like this in height, so 50 centimeters or something like that. And he could really do motions that were not possible until then, so he felt really like you were interacting with real humanoid being.
So in 2013, NASA and Boston Dynamics, they created 2 life-size robots that were designed to operate in hazardous environments. And you can see the Atlas here from Boston Dynamics, and it received a lot of media coverage for its flexibility, its size, its strength, and so on. And there was one commentator announcing the arrival of a new species, the Robo Sapiens.
So in 2016, Boston Dynamics built Spot and Spot Mini. You can buy them if you have the money. It's not very cheap. They walk on 4 legs, like a robotic dog. And if you watch it walking, it's also a little bit scary, I think. Who knows the Black Mirror episode? Yeah. So it's looking quite natural already, but it's also a little bit scary.
All right, and then in 2023, there were the first robots who could really control somehow the environment by giving it natural instructions. So the RT2 was the first robot with which you could just say, put the banana on number 3 or something like that. And it really followed these movements and tried to make that happen. Now?
Okay, and last year, the Chinese company Unitree created a product, namely this guy, right? He's a very nice chap. You can buy him for 20 to 40,000 US dollars. And of course, he's all smiles on the outside. And on the inside, you find lots of amazing technology like AI, amazing sensors, security vulnerabilities, and so on. And then this year, we have seen the release of many very cool open source robotics do-it-yourself kits that you can assemble at home to get in touch with state-of-the-art robotics technology, like the SO101, which is what you can see here, and we'll talk more about it later. Right, so I think we're done with the timeline section.
Yeah, absolutely. And we want to talk about why are we talking about this now? Yeah, the thing is, why is the robotics revolution starting at this very moment? And you know that it's been in the news. So whenever Jensen Huang is doing a keynote, there's robots with him on stage, same as with us, of course. And they are also running marathons in China, so it's getting more and more into the field of into the lives of normal people. So normal people will experience these robots in the future as well. So you can do it today, but the normal people will do it tomorrow when we go to the Deutsches Museum or something like that and let him walk around a little bit. But the things tend to get interesting when we talk about everyday tasks. So, for example, if you have a look at this example from Pi0, which is a robotic foundational model, we'll talk about it a little bit later, then you can see that these robots now really start to do something useful, like fold our laundry and do some chores that we would normally not like to do, but have to do. And this is where things get interesting.
All right, so there will be more and more humanoids, and the question is, what will we be using them for, right? And unfortunately, the first thing that comes to people's mind is we'll use them as war machines, because that's how Hollywood has raised us. But there are much more optimistic outlooks as well. For example, we can use robots in disaster response. Imagine as a burning factory or something like that, and you don't want to wait for the fire brigade, and you don't even want to send in people, but maybe there's an android nearby that can just go in there without putting anyone in danger and close that valve and rescue us all, right? So that's one disaster they could help out with, and there's another disaster where they could be really useful, namely the loneliness epidemic, right? So especially in countries with an ever-aging population, we see more and more concepts how these humanoids could provide companionship and take care of the elderly.
It's not scary at all.
So when I showed this image to my son, he said, "Oh, very cool." But actually, that robot doesn't look very social. And I think he's right there. And these androids, they still have a way to go if they want to cross the so-called uncanny valley. Right? This uncanny valley is a regime where something resembles a human being, but not quite so. So you find it kind of like eerie, and you feel repelled from it, actually. But as the technology progresses and they resemble humans more and more, I think it is conceivable that it will become more and more acceptable for us to live with these humanoids in our own households. And actually, there are already a lot of people who live with a robot in a household. For example, like the vacuum cleaner, the little thing that sweeps the floor. And as technology progresses, they could maybe also take over more tasks that are still reserved to us, like Thomas said, doing the laundry or cleaning the dishes and so on. And obviously, they will probably also replace human labor, right? Especially where it's strenuous in warehouses, for example, because then they could carry heavier weights than we can, and they don't need a break, and so on. And that's why investment companies, for example, like Morgan Stanley, are extremely bullish about the Android market. They say in 2050, it could be up to $5 trillion US, and we will live with 1 billion humanoid robots working in our factories or in our homes. And other companies are less excited. So for example, the advisory firm Gartner finds that humanoid robots are being heavily promoted, but practical applications are almost unknown. Product leaders should seek other polyfunctional form factors which will deliver better value at lower cost. So what they're saying is that robots that are purposefully designed to perform a specific task, they will have a greater impact than a robot that looks like a human for the sake of looking like a human. So this confusion, people being very enthusiastic and others being skeptical, is very typical for the phase in which we're in the so-called hype cycle, right? At the beginning, these humanoids are innovation triggers. They spark a lot of imagination and money flows into this market. But after this peak of inflated expectations, a lot of non-working ideas become abandoned, and other ideas might prevail, and they become more and more refined, and they slowly produce more and more actual value. And so, does it mean that for now, robots are only entertaining, they only serve to make hilarious presentations? And I would like to give you an example of where this is definitely not the case, where robots have a real impact on the quality of life of some people. Right, this girl here is called Tilly Lockie, and she has both her forearms amputated. And so she's using these prosthetic arms here, which I think are extremely convincing. They do look like real hands, save the color, and she's able to move them like she's moving any other body part by her will, right? So as if it is her own musculature. And she can use these to grab objects, and I think it's really amazing technology. And it is, in part, technology that will be presented today. So let's dive in understanding some more of basic robotics.
Let's start with robot basics. And what do we need for a robot, to build such a robot? Most important, we need an energy source, right? That could be batteries, but that it's unfortunate that you don't see the video now, but usually you would see a video of that Wildcat robot, which has an internal combustion engine and which is pretty loud, probably really stinks and is really harmful for the environment. And fortunately, we are more advanced now. We have lithium batteries. They are pretty much available. They are getting cheaper. So I would say most mobile robots are now powered by lithium batteries, of course. Okay, what else do we need? We need something so that the robot can interact with its environment, right? Some actuators, they are called. So, or some just call them motors. So your vacuum cleaner has some wheels and a motor attached to it so that the robot can can drive around your home. But there are also robotic arms so that the robot can grip something and pick something up. And this is a joint of the G1 robot. It looks a little bit older already. Oh. Yeah, I think it was worth it. So imagine, imagine that thing now cleaning your dishes. And yeah. So yeah, luckily we have other solutions now. I was talking about motors and actuators. So this thing looks quite simple from the outside, and you would think it's just a motor. But actually, you saw the image. It contains a lot of other mechanical components, like a gear, right? Sometimes brakes for industrial robots, decoders so that the robot can determine the joint positions. Of course, some electronics for driving the motor as well. And I think those are also one of the most expensive parts in such a robot. Especially in humanoids, because you have around 30 robots there. And compared to such a robotic arm, which we will see later, they only have 6, 7 joints and are much cheaper there. Okay, so we have energy, we have something to interact with the world. Now we need to see the world, right? And a simple solution for that would be cameras or even 3D cameras. But there are also more complex things. Also the G1, our robot here, has such a thing. It's called a LiDAR. It's a thing where you have a laser device which can measure the distance to a certain object, right? And now you scan the laser over a certain area, and then you get a 3D point cloud, basically a 3D model of your environments and your surrounding. And on the right side here, you can see the result of such a LiDAR scan. And G1 does this multiple times a second and gets a really good feeling of his environment. And last but not least, we need something like a brain, right, to read out the sensors and, of course, to control the motors. basically small computers. One system which is really important on the market, or really well placed on the market, it's the NVIDIA Jetson. It's an embedded system with a processing unit, but also a GPU, so that it can run simple, small AI models. And it's also quite, it's small and it doesn't use too much power. Okay, and Sven, now what does run on this brain?
All right, so we want to talk about 2 to 3 algorithms that these robots have to perform. And the first one they do, or that we want to talk about, is called simultaneous localization and mapping, or SLAM. And the robot uses it in order to orient itself in its environment. And let's see how this works. So assume there's a robot and it's in a room, right? And there's an obstacle in this room, for example, Florian. And for the sake of argument, let's assume Florian is a square. So the robot wants to move through the room. And before it does it, it has to make sure not to run into an obstacle, so it does take a sensor reading. And it finds obstacles, which are indicated here as these solid orange lines. And from that data, it can create an internal map, which is here on the right-hand side. And it also has an idea of its relative position to its obstacles, so it can put itself on that map. And now as the robot moves through the room, it can update its own position on the map, but it can only do so with some uncertainty. And that's because that even if you think that you make one step and it's exactly 50 centimeters, maybe there's a slope, so you can't really know that you really move these 50 centimeters. Also, there's some sensor noise coming from the motors and so on. So it's a small error, but the more the robot moves, that error compounds and it becomes very large. So what it can do is it can take a second reading of its environment at that new position, and then on this new data, find pieces of information that it has already seen on the previous data, right, which are these red rectangles. And it can use that information again to put the new data on top of the second data and create a more complete map. That's the mapping part. And it can also use that data to get a more accurate estimate of its position. And that's the localization part in SLAM. And as the robot crosses the room more and more, it gets a more accurate map and also a more accurate position estimate. Okay, and here's an example of SLAM in action for a vacuuming robot. On the top right, you see an optical camera, which is mounted onto the robot as it is sweeping the floor. And in the big picture here, you see the LiDAR data, these point clouds that are slowly forming a map. Okay, and I could look at this all day, but I don't want to fall asleep. So let's talk about the second algorithm. It's motion planning. So assume you want your robot to look over its left shoulder, right? And you tell it to do so, and it does this. So it's obviously correct. It's obviously correct, but not what we wanted it to do. We wanted it to take the short way, because the short way is faster and it's more efficient, takes less energy. And so it's very easy to solve the motion planning problem if you only have 1 degree of freedom. But if you have many degrees of freedom, it becomes much more difficult. And one problem that is related to these many degrees of freedoms is called inverse kinematics. And to explain that, we look at the arm of the G1 PO, which is here. And now I want the robot to grab something. And if I wanted to grab something, I'm basically interested in the position of its gripper here, right? So if I wanted to go there, I need to place its fingers there. And it has 3 fingertips, and each fingertip has 3 coordinates, x, y, z. So that's in total 9 coordinates for the gripper pose. But we don't control the pose, we control the joints. So each joint has a given angle, and when I counted it, maybe somebody counted a different number, but I counted 13 relevant joints in order to move the pose. And going from the joints to the gripper pose, it's a straightforward problem. It's called forward kinematics. You can just solve it geometrically. But going the other way around, which is called inverse kinematics, it's a much more complex problem. And you see here why, because you have 9 coordinates for the pose, from which you have to estimate 13 coordinates for the joints, so the problem is underdefined. And what you have to do is you have to use some mathematical solvers. There are no generic solutions to finding this problem. And these solvers, they are already always designed specifically for a given geometry. And I have to make sure like not to move these joints through forbidden angles, right? If I move my finger too far in that direction, it breaks. And it also must make sure not to try to grab through its own body. Okay, so that's inverse kinematics. You have to solve it a lot of times, right? Because if you're updating or if you're moving from A to B, you have to do many, many updates and so on. And that's how we covered like 3 basic algorithms. And let's see some much more complex algorithm. And let's talk about training our robot.
Yeah, let's talk about training a little bit. And of course, now we can finally get some fun AI slop. I put a lot of work into that. All right. How do we control a robot? So with the inverse kinematics that we just learned about, so basically we can then say, let's put the robot into a specific pose. Let's just say we want the arm stretched out or something like that. The inverse kinematics solver will solve that for us. It will bring it to this position, and with that we can then grab something in a hard-coded way. So for example, if we know exactly where an object is located, we can then pick it up and place it somewhere else. But this is pretty boring. This is not what we want to do, right? So we want something that can solve an arbitrary problem. So for example, if I'm walking around, I don't want to control every joint at every point in time, because there might be something lying on the floor and then my robot will basically just fall down. And this is something I really need to avoid. And but for the sake of it, we can just do already amazing things with this. So for example, we can make our robot dance. Which is pretty cool, right? But nevertheless, it's not what we want to do. So let's take an example. So we want to train our robot. We want to send him to the gym to really learn how to walk by itself and without any Chinese algorithms involved that we have right now. So let's do that. Let's send it to the gym. And what we want to do is we want to do some reinforcement learning. So reinforcement learning basically works like this. So you have a robot. This robot is situated somewhere. So it's here in the real world, interacting with its environment. And it can do so by doing many actions. So we can just say do some random action or something like that at the beginning. And then we will then interpret the behavior. We will see what the robot is doing, and we can give some rewards or punishments for these actions. So if the robot is, for example, just staying in a fixed position, that might be too boring, so we punish it for this behavior. Or exactly like that. Or if it falls down, please don't do that. Then we will also punish it for this behavior. But if the robot walks in a straight line, and there's some cables there, so please don't do that as well, then we will reward it for this. And if it stays up long enough, we will accumulate some rewards, and based on that, it will learn how to do this. And in order to do this, we need something that is capable of learning, and these are nowadays, of course, neural networks, so deep neural networks that you can train on these rewards, and with that, it will then work with these rewards and try to get better and better in time, and try to actually learn how to walk. Of course, we are not doing this with our robot itself, because that would cost us a lot of money if we did this. So normally what we do is we send it to a simulation environment. So what you can see here is Isaac Lab from NVIDIA, and there are some models to it. It also has some physics simulation ingrained in there, and if we just let the robot spawn there, it will basically, so the only thing it does, so it does not know what to do, it has not learned anything yet, so it will just stay in place. And unfortunately, staying in place means that eventually it's falling down, right? And this is what happens here. So the robot falls down, gets up again, falls down, gets up again, and so on, and so on, and so on. And it is continuously punished for this behavior because we don't want it to fall down all the time. And since we also want it to learn faster, we are not doing this with one robot at the same time, but 4,000 at the same time. And also, if we just switch off the visual feedback, then it will also be a little bit faster. And after some hours of training, we have like 100 epochs behind us, so it will have learned to avoid the behavior which will be punished, and at the same time it will try to mimic the behavior that is rewarded. And this will then lead to something like that. So now it's walking, but at some point in time it still falls down, so it randomly still happens. And then at 200 epochs we finally learned how to walk, and with that we are in a good position. And now what we need to do next is we need to bring that to the real world. So we need to map that simulation behavior that we have to the real joints. And if we do that correctly, then something magical will happen and we will have something like that. And
now it's working.
Here you can also see it on the video. It still looks a little bit drunk, but it's walking right now. All right. With that, we'll get to the robot foundational models.
Yeah. So now we've learned how to teach the robot one thing, like walking or doing another specific specific task. But well, we want to help us in our kitchen. Yeah, folding laundry, doing a lot of different tasks around the world, right? And we probably cannot afford to generate policy or train policies for all of those tasks. What we want to have is a more generic solution to all of those tasks. And
therefore, we have our robotic foundational models and some AI slop.
The slop.
Claro, puedo ayudarte con eso. Too many modalities.
Exactly. So, robotics foundational models, they are pretty new and they, are promising us to have a solution for that problem, or be one solution. It's a little bit like, it's a tool a little bit like large language models, right? So they have some knowledge about the world, right? And we can make use of that knowledge, and it's pretty similar with them. Okay, and by the way, there was a talk some hours ago in this room, so if you missed it, it was specific to robotics foundational models. So if you're interested in that topic, please look it up later on YouTube. Okay. So now my speaker slides would be interesting, but there are different open source versions of robotics foundational models like Pi0 or again NVIDIA, NVIDIA Groot N1.5. And let's maybe have a quick look at how such a robotics foundational model work, right? So all of them take as an input images the robot takes itself with the cameras, also a prompt, a language instruction, because we want to give it a specific task. In this case, pick up a dice and move it to the plate, and also the robotic state. And then they do some magic, the vision language model, diffusion transformer, I will come to that later. And the output is a set of motor actions. Not a single motor action, but rather multiple motor actions for specific timestamps, like 15 points in time, which is called a trajectory. Okay, and what's happening in between? There are, in most RFM architectures, there are two components. One is the vision language model, which takes care of organizing the high-level task, right? It takes care of understanding the image, understanding the language instruction, and then generates some kind of vector which will be used by the next step, the diffusion transformer, to then generate the actions. Okay. The vision language model is pretty generic, right? It just it's mostly trained on data, on video data. So it basically gets an understanding of how images are processed, and also on language data, right? Not that much on the robotic. It does not have a real good understanding of robotic motions. Okay, but those models are pretty huge. So they have billions of parameters. So the GROOT N 1.5 has 3 billion parameters. It's not as much as the large language models we usually have, but still a lot of parameters, and you need to have a lot of training data for that. And we know from papers what NVIDIA did for that, what training data did they use. So they basically scraped the internet for videos to train the VLM part, and also some text from the internet to train the language understanding part. But they also used a lot of synthetic data, because the problem is really getting good, high-quality data for robotic trajectories. That's a missing piece. And they also found pretty amazing solutions for that. So they also used human videos, like on the left side, where they had a camera mounted on the head of a human. And the human just did some tasks. And then they used an AI model to generate trajectories from that video. It's a pretty cheap way to get good trajectories, right? They're not perfect they're not as good as if the robot would have taken them themselves, but it's a good intermediate step. Then there is synthetic robot data, which they also used, and it's basically there are special models like DreamGen, they are called, from NVIDIA, where the robot, you give it a prompt, and then the model dreams videos, artificially generates videos and also trajectories of robots executing tasks. And of course, at the peak of this pyramid, there is also some real-world robot data, but the data set there is 10 times smaller than, for example, the synthetic robot data, and the web data is just large. Okay, so now we have that RFM. We can download it from NVIDIA or Hugging Face. And then we need to, it's not specific to a certain robot. So the idea behind the robotic foundation model is you can use it on your humanoid robot, you can use it on a robotic arm, different amount of joints, different configurations, different camera setups, right? So there's one last step needed. You need to fine-tune this open source robotics foundation model to your concrete robotic setup. And you do that by taking some training data. We will show you later how we do that. And then you need some training steps. And in order to not need to train the whole or retrain the whole model, you freeze certain parts. For example, this vision language part, I said it's pretty generic. So what we do there, we freeze the weights, we don't touch that. Interestingly, this is also sometimes true for the diffusion transformer. So for the demos we will show you, we froze the diffusion transformer there as well. So here we just trained the encoder and inside the decoder. So that means inside those two components, something like the embodiment of or it's called the embodiment of the robot is stored, that information is stored there. And that training, well, it takes a few hours, but retraining the whole model would take a lot longer. Okay, Sven.
All right, so now you want to train your own robotic foundation model, but you don't want to spend like $40,000 for your own humanoid. Or maybe you did spend it and it broke. So in that case, we have something for you, and that's called Le Robot, which is a very cool company that's now part of Hugging Face. And what they do is they produce these open source robotic kits that you can then build at home. And not only that, thank you, Thomas, they also provide the software that you need in order to run robotic foundation models for your robot, like Groot or Pi0. So let's build this guy, the SO101. It's a robotic arm. I think that was released a couple of months ago, and we decided for this guy because it can grab stuff and we can play lots of funny games with it. What do you need in order to construct it? Just a couple of parts, a couple of motors, a camera, plastic pieces that come out of your 3D printer, and all these together, they cost you only 120 euros. So it's actually pretty cheap. The most expensive part is the GPU that you need for training your model, for fine-tuning, or maybe to do the inference. We are using an RTX 4090, which costs about 2,000 euros, so it's a bit expensive. But if you don't want to spend the money up front, you can also get a GPU from some cloud provider. All right, and let's do a little demo now to show you.
So we have two S101 in the so-called follower configuration, and we have two in the leader configuration, right? So the leader, I can take the leader, the leader robot, and the follower basically follows the movements of the leader, right? And I can now try to, it's a little bit difficult because, yeah. Standing good 90 degrees, it's not making things. And also someone modified the gripper, so now it's very slippery. So.
It's always somebody else's fault.
Yeah. But yeah, I think you get the gist. So
the game that we want to play is we put the yellow dice on the left saucer and the red dice on the right saucer. And yeah, it's a basic game for the beginning, but if you come back next year, we hope to be able to show you open heart surgery.
Yeah, we need volunteers, exactly.
You can sign up later. Yeah.
All right.
So we're going back to the presentation now.
All right. So if you think that this little presentation that we did was pretty basic and you cannot do that for a humanoid robot or something like that, you are absolutely wrong, because you can actually do this. And you can use Apple Vision Pro, which you can buy for another cheap 4,000 euros or something like that. And with that, you can then control the robot as well. And in this case, you don't have a leader-follower principle. You just use your arms, and the robot does exactly the same thing. And with that, you can also just do some imitation learning by recording some sequences and using that for training purposes as well. All right, and of course, one thing we forgot, we don't want to do everything on our own as well. So again, we have a simulation environment that we can use, and within this simulation environment, we have all the ingredients. So there's also the virtual cameras, which are attached to the robots, and these will also provide us with some images that will be fed to the robotic foundation model as well. And then we have the dice, we have the physics simulation, which will then simulate our environment, and with that we can train a robotic foundational model. And if everything works well, we get something like this in the end. So you can see that it really tries to basically break itself. So this is exactly what we were aiming for. So this is the result, by the way. Yes, so if you do the mapping correctly and if everything works out in the end, you will also be able to translate the simulation results to the real world, and then it will rather look something like this one, where we can now pick things up and put them somewhere. And as you can see, the yellow dice go in this saucer and the red dice in the other saucer. All right. So it will have learned the exact same behavior, and we can do this for something we saw earlier today as well. So for example, if we want to do some folding of laundry, you can see that it's not perfect. It's not as perfect as the one we saw before, but it at least tried to do that. And
And keep in mind, it's just 240 euros plus a graphics card, and you can use that at home.
Yeah, but Florian, this is still wobbling around a little bit. So a little bit. Can we do something about that?
Yeah, we can. We certainly can. So what we need to do there, or let me first explain why does it do this wobbly movements. So what we do right now in the simple case is we have some trajectory predicted by the robotic foundation model, and our robot follows it. And then if the trajectory is done, we will start the inference. We will stop the movement, start the inference. It will take some milliseconds, and afterwards we have the predicted trajectory, and we follow it again. So and so on and so forth. So we will always have that pauses inside our movements. And the question is now, can we do it differently? Can we, for example, start the inference while the robot is still moving? And something like that. And that, in theory, works. But there are some problems with it. So one thing is, it's very likely that the new trajectory has a slightly different path, so you will probably never hit the right onset point. Also, the movement will not be smooth because it's not continuous. What you could do there is you could do smoothing, right, of the trajectory, and then you have that problem solved. However, there are certain edge cases, like, for example, if you have an obstacle. Sorry, Sven. And because what could happen there is the AFM at the beginning of the inference decides to move to use a completely different path now around Sven, because Sven is so big. And what would happen now if we smooth? Yeah, sorry, that wouldn't end up good for Sven. So we need to have a different solution because we want to keep our Sven. And the solution is actually pretty easy because it's even simpler than finding a good averaging algorithm for the smoothing of the movements. And it's inspired by image generation models. So what we basically do is we do in-painting. What is in-painting? In-painting is, well, you have some image and you want to alter the image with a prompt. The prompt here could be, for example, I want to have a cat in the image. But I want to have the cat at a specific area of the image. And what we do there is we give the image generation model not only the source image, but also a mask where it is allowed to replace pixels. And then we get a nice image of the cat somewhere in the nature. And we just do it like that. So we give the diffusion transformer the information, okay, certain items of, certain parts of the result should be fixed at certain positions, right? And then the AFM already guarantees that this trajectory is smooth. And then Sven is safe. And we can try that now. It's live. Oh.
Oh no.
They are not slippery at all, so you lied to us.
That's too close. That's too far. I don't think it is a good idea to make this gripper that slippery. Ah.
So who's up for open heart surgery?
The interesting part here is, or one interesting thing here is we don't have any for loop. So so we don't have a for loop like, okay, for every dice in the area, please. Yeah.
Yeah!
Yeah, he's nervous. But in the exhibition area, we have a robot, the same setup with a better gripper. Let's wait for a second one. Yeah.
Yay!
Okay.
Oh, he's
Yeah.
having a run.
Oh, now he's having a roll. Come on. Ooh.
Heard you talking shit.
And now the only thing that's left to do, and the only thing, is to really bring that back to the big robots. And there is a project going on which is called AMO, or Adaptive Motion Optimization. And with that one, we can have some high-level tasks like pick up the baskets and put them on the shelf. And then the robot will do some pretty complex stuff like picking up the baskets, then walking over to the shelf and then putting them on the shelf. So you can do that as well with the robots. So that leaves us with our final slide. So the future might be something like in the iRobot movie from the year 2004. So there we have delivery drones and drones that kill you on occasion. And this is actually a scene that was shot in Chicago in 2035, but I think it could as well be in Munich. So thank you.
Thank you, guys. Oh, sorry, G1 PO, I'm in the way. Thanks a lot, guys. That was a great talk. Now we have time for questions, but of course, if you're super hungry, feel free to skip them, but I think there could be some interesting ones. I have a first one, if you still need time to think of all the stuff you just saw. I'm very impressed. So the first thing I have to say, what immediately jumped to my mind is, you talked about the sourcing of this robot, right? It's Chinese, right? And you kind of alluded to this being maybe a risk, right? If robots are more and more integrated into our society, they can become critical infrastructure, right? Do we need German or European robots?
We definitely do, I would say. So it's very important for us to have robots where we know what they are doing. And there are some robots that also are already in development. So there are some companies like Neura that are currently developing those robots. Unfortunately, somehow the Chinese are building these things pretty cheaply. So that's also the reason why they broke down a few times. But nevertheless, you can get a robot for 20,000 euros, and we have to come to a point where this is also possible with robots that we can build here, that we can source from a local source where we also know how that it is somehow compliant to the GDPR or something like that.
And there are also nowadays open source humanoid robots. So my goal for the next big tech day is to bring an open source humanoid here.
Okay,
That's
Something to
that
look
was
forward to,
on
right?
record, right?
Yeah.
Amazing. Feel free, like if you have questions. Yeah, there we go. Let's start with you and then go with 3.
Thanks a lot.
Adam Waugh from Takeda, technology lead for robotics. We are in the pharmaceutical industry, so my question goes a bit in the direction of application areas, use cases that you see in any industry or even in real-life scenarios in service robotics for foundation models.
Yep. So the real-life scenarios of these, we brought a few of the real-life scenarios with us today. I think for now, we need to be a little bit humble. So this one was already one of the more complex scenarios that we could come up with these robotic foundational models. And actually, I think within the next few years we will see some pretty experimental use cases where we can use them. For example, handing over different parts of maybe automobile in a factory or something like that. So this might be something that is working with the technology that we have at hand today. If we really want to get to a robot delivering packages to your doorstep, that's still gonna take a little bit of time, and it's still gonna need a lot more technology than we have today. But in the end, LLMs were at this place like something like 7 years ago, so nobody thought that it would be possible to come up with something useful, that a neural network would even be able to simulate the natural language. And nowadays we have ChatGPT and things like that. So if there is enough money in it, if there are new companies training on this data, if there are clever tricks to come up with training data as well, like we have seen with the inverse dynamics thing, then I think at some point we will end up with something that is that can really walk the human environment and at the same time do something useful.
Thank you. Let's hope for that breakthrough.
So, and I mean, as Thomas said, robotics foundation models are a really young technology, right? So, I mean, last year RT1, and now Groot and Pi Zero is from 2025, right? So, and also what I find really fascinating is you can build that at your home without going bankrupt.
So one of the things, I guess, is that was it G1 PO is his name?
Yeah.
I guess he doesn't do. Yes, hello. I guess he doesn't do his inference in house, but that's rather done on a remote system. So the question is, do you reckon that humanoid robots in the world will inevitably be doing all their inference remotely, so that essentially we're streaming data everywhere?
I don't know. So the thing is, this robot has a built-in NVIDIA Jetson GPU, and this NVIDIA Jetson GPU can be easily powered by the power supply that we have in there, and this is already capable of doing some basic tasks with neural networks. And in the future, I think that the hardware will still get smaller, and it will be easier to come up with a small form factor that at the same time is powerful enough to power some more advanced applications as well. So we saw today that the Groot model is something like 3.5 billion parameters in total, and this is something that you could run on a smaller machine. I think that the more advanced the things get, the more tokens they will probably need at some point in time. But at the same time, the technology is evolving. We have the DGX computers right now, which also have a pretty small form factor for what they are capable of doing. So I think that this will, in the end, probably run on the edge, so on this edge, and it will probably work out pretty fine.
Yeah. And maybe some computational tasks will be outsourced to some kind of cloud, but most of the, also for latency reasons, right? So the RFM model we have there, it runs with 30 hertz, and latency is really crucial here. If you have latency more than 200 milliseconds in your loop, then you cannot basically use the robot anymore. So.
Very cool. Hey, thanks a lot. Again, thank you to our speakers.